Okay, well, welcome back, everyone. Um, we continue our journey into the effort of revisiting classical mechanics. Um, Remember, we are doing this for two main reasons before we enter the discussion about quantum mechanics. The first reason is that of refreshing some fundamental concepts, which will turn out to be key also in the quantum mechanical description. It turns out that while some aspects of classical mechanics are abandoned in the transition from classical to quantum realm, such as the Newton's equations, for instance, some concepts that have been developed in quantum mechanics, in classical mechanics, such as the concept of energy, momentum, angular momentum, turn out to be more general than their particular realization in classical mechanics, and therefore are actually naturally transferred into the quantum mechanical theory. So they will be there also in quantum mechanics, and in some cases they will play a crucial role in the application of quantum mechanics to chemistry and to many electron systems in general, many quantum particle systems. And this will be the concept of angular momentum, for instance. So in the previous lecture, we have introduced this concept, which I'm just going to list. Energy and its conservation, total momentum and its conservation, and angular momentum and its conservation. And all of these three elements will become important also in quantum mechanics. And in fact, in modern physics, these three conservation laws has been understood at a much deeper level as a reflection of fundamental properties of space-time, but we'll not go into that detail in this course. But what I'm trying to say is that there is something far deeper than Newton's equations that leads to this conservation. And this is the ultimate reason why the same conservation laws are found also within the context of quantum mechanics. The second goal while we do this, while we review classical mechanics, is to begin making some predictions which ultimately set the stage for introducing quantum mechanics. In particular, what we're going to be doing today is to attempt building a theory for the simplest atom you could think of, hydrogen atom, entirely within the concept of classical mechanics. We will build a classical theory for the hydrogen atom. And we will discover that it is impossible that classical mechanics is holding true at the atomic scale, because it would predict that the hydrogen atom would be very unstable. It would basically collapse, the electron would collapse into the proton within femtoseconds. So there's no actual way you can make sense of the hydrogen atom, which we know to have that structure from experiments. So there's no way you can make sense of these experiments within the framework of classical mechanics alone. And this will be the first case of many we will encounter later, in which we understand how classical mechanics breaks down at the atomic scale. So the purpose of today's lectures is in fact that of revisiting and making a classical theory of the hydrogen atom. And we will do that, but to do that, we will use very extensively the concepts of conservations that we have used previously, we introduced or reviewed previously in this course. So let's assume we have sufficient experimental information available to know that, the structure of the hydrogen atom is one in which I have a charge point particle in the center and a negatively charged particle, the electron, orbiting sort of around the center. Now, this information actually comes from a number of experiments, like I said before, in particular the Rutherford experiments. I will not go into these details of how this structural information has been gathered over the different experiments. I will assume this is the structure of the atom we know, and I will try to build a theory starting from Newton's equation. So just to give you some detail, the mass of the electron, which I will denote here, the small m. So the mass of the atom, the electron, and small m, divided by the mass of the proton, is roughly speaking 1/2000. Which basically means that the center of mass of the system is very close to the nucleus. And we can assume in first approximation that the nucleus doesn't move. It remains still, it has infinite mass, and the electron will orbit it. Now, you can get rid of this simplifying assumption by going to relative coordinates. That is an unnecessary complication at this stage, because the point of the lecture wouldn't change. You just have to work with reduced masses and make things slightly more complicated. If you want to account for the fact that the nucleus has a finite mass and can move a little bit when the electron orbits around, right? We will neglect this motion because it's extremely small motion. You can draw like a small circle here because of these differences in mass. The second point I want to make is that, of course, the charge of the proton is the negative of the charge of the electron. So let me take it away from here, which we know. So overall, the system is neutral. And finally, we will neglect any size of either the proton or the electron. Well, the electron is considered point-like even at today's standards because no experiment was ever able to resolve an inner structure of the electron. So that's not considered to be a strong approximation. It's actually exact to the point that no experiment today was able to resolve any structure, meaning that the electron, if it has a finite size, and therefore it's a composite object, it has a size that is smaller than the smallest scale ever explored by humanity in their experiments. On the other hand, like we said the other time, the mass of the radius of the proton is roughly speaking 10 to the minus 15 meters, whether the radius is typically 10 to the minus 10. So for all practical purposes, we can regard the proton too to be point-like. So point-like protons. So these are three things we're going to keep using and keep in mind while developing a classical theory for the hydrogen atom. Okay. While we do that, that's the natural way to start this discussion would be Newton's equation, obviously. So let's start writing Newton's equation. We have the mass of the electron times the double derivative with respect to time of the electron position. Normally I used the notation x to denote the position. This time, for reasons that will become clear in a minute, I'd rather use the notation r, because I'm going to go into polar coordinates very soon. And this is, of course, the force that is acting on the electron because of the attraction with by the proton, exerted by the proton. So what I would have to do is to put negative of the unitary vector pointing from the proton in the direction of the electron. It's an attractive force, and therefore is going inwards, hence the negative sign. Because the force, really, the Coulomb attraction goes in this direction, right? So it is opposite with respect to the distance between the proton and the electron. Then I will get the E squared and then depending on what units you use, you might have a 4 pi epsilon squared downstairs, epsilon naught. This is in the international units, or so-called MKS units. I will consider a slightly different set of units called the CGS units, where there is no such a thing denominator. Normally, quantum mechanics is formulated in CGS units. So it's slightly different set of units, which comes useful when doing calculations because you don't want to carry around this 4 pi epsilon naught. So if you don't remember about this 4 pi epsilon naught, go back on your electrostatics book. You'll discover the structure of the Newton's law has such factors floating around. We neglect them because we work in units where these factors are absorbed in the definition of things. You don't need really to go very far in understanding this. You just have to say that this is a good expression for the force and move on from that. Okay, so the first observation is that this is not actually a single equation, is in fact 3 different equations, right? Because if I was to very pedantically spell out this equation, I would have to say mass second derivative with respect to time of the x coordinates, second derivative with respect to time of the y coordinate, and second derivative with respect to time of the z coordinate, where r is supposed to be x, y, and z, 3 Cartesian coordinates of the position of the electron. And on the right hand side, I would have that's my force, right there. And I would have the x component of the force, the y component of the force, and the z component of the force, which depends on the entire 3 components. So let me say x, y, z. This is x, y, z, and this is x, y, z. Now, since x, y, and z are actually, let me be more explicit, varying with time because the electron is moving, I should say x of t, y of t, z of t, and do the same for all of them. So, as you can see, the problem is quite complicated because in order to understand the motion of an electron around the nucleus, you have to solve 3 differential equations. But you see, these differential equations are pretty nasty because in order to say solve the first one, you want to solve for the function x of t, you need y of t and z of t, because without y and t and z of t, you cannot solve this equation, let alone the difficulty of solving single differential equations, which are not particularly simple, which is not particularly simple to solve. You don't even have the ingredients to solve it because you need to know the motion of the y and z component to be even able to write this equation. Likewise, suppose you want to solve for the y component, so that's here, you would have to solve for the x and z component. And not surprisingly, suppose you want to solve for the z component, you miss the x and y components. So altogether, you have three equations for three functions, x of t, y of t, z of t, but these three equations are coupled, which means that you cannot solve it one at a time independently for the other. You have to find a way to solve them all together. So, as you can see, whenever you look at the problem for multidimensional motion in classical mechanics, you face the problem of solving coupled second-order differential equations, which is, of course, not a simple problem to solve. Most of the course that will be presented next year by Diana, I think, for sure even Lattanzi. But anyway, you see, I think Diana and Lattanzi will be focused on molecular simulations, which are based on computational engine or algorithms that are able to numerically solve coupled differential equations. And you can go as far as solving 500,000 or 1 million coupled differential equations for many, 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 many time steps in forward in time and getting the evolution, say, of macromolecules. So using contemporary computer or supercomputers, I should say, you can actually address the problem of solving coupled differential equations quite efficiently, and you will be taught about these methods next year. But in this year, we stick to, but in this discussion, we want to get something at the more basic fundamental level without having to invoke computers. So you immediately see that it is a horrible problem, even the simplest problem of a particle interacting with a point, right? However, there's a way around, and this way around makes us use of the concept of conservation of energy and angular momentum that we introduced in the previous lectures. So you can begin to see how powerful and far-reaching those ideas are when it really comes to solving problems. So the idea is to introduce polar coordinates. Now, this is a general thing, general discussion in physics. The choice of how you choose to mathematically formulate a problem in physics is not unique. You can choose your axis, for instance. This is something we are familiar with. For instance, I guess everyone in this room has ever taken the problem of a particle rolling down a cliff, point particle interacting with a gravitational field going down a cliff. And one of the reasons this is a useful exercise is because you soon realize that depending on how you fix your axis, for instance, you get different descriptions. They are all equivalent, but not all equally simple. For instance, if you choose to set the x-axis here and the y-axis this way, the trajectory is a combination, non-trivial combination of two motions, one of the y component and one of the x component, right? So you have to solve two non-trivial equations and combine them together to discover that a particle is moving along the straight line in this component, in this direction. However, I guess you all had the experience that if you choose different, you make a different choice for your axis, for instance, you put one here and one here. You immediately realize that with respect to this axis, this particle is not changing its y prime position because it's not going inside the wall or the ground. So the motion of the y prime coordinate is trivial. Y prime stays constant, maybe equal to 0 in this case. So all you have to do is to solve one differential equation, the one for x prime, which will tell you how far you're accelerating with respect to a frame that is set on the cliff. Now you see the amount of physical information in these two representations is completely equivalent, but the work you need to do to reach that information, to gain information, is very different. In one case, you have to solve two differential equations, get the motion of the x and y, and then, if you want, use Pythagoras' law to understand how far you're moving from the initial point along the cliff. In the second case, you only have to solve one differential equation, and already from the trivial one, y prime equal to 0, you get for free that the system is moving in a straight line. So why is it that choosing different coordinate systems, I get different degrees of mathematical involvement in the problem? The reason is that in the first choice, the one that I was setting the axis according to the, say, level of the ground, say I'm saying this choice, I was not fully making use of the symmetry of the problem. The problem has an intrinsic symmetry, which is if you move along the cliff, the structure of the system doesn't change. While if you move along the x-axis, the height of the cliff changes as you propagate along the x-axis. So that's not a natural symmetry of the system. We call it a symmetry, something like I perform a change in the system and nothing changes. Give you an example, you take your basketball. This is a basketball. Now imagine for a moment to have the basketball evenly colored on a color so well that you cannot distinguish. It's completely leveled and nicely covered. If I were to make a rotation by some degrees, you will not be able to notice it because the ball would be perfectly homogeneously painted all over. This would be a symmetry of the problem. Making a transformation doesn't change the results. The system is invariant under this transformation. Now, this very basketball is not invariant because it has stripes. So if I make a slight rotation, you can detect this rotation because you see a slight stripe is moving in the direction. So this example of the basketball shows whenever you have a symmetry or when you have something that breaks that symmetry and makes it physical. So why am I telling all this about symmetry? Because now we are equipped to go back to our hydrogen atom problem. And the moral of the story is that we should always try to use the coordinates that make the most use of the existing symmetry in the problem. So in this case, I have a proton staying in the middle, I have an electron. And remember, the position R is going from the center of the proton to the electron because I'm setting my origin in the proton. That makes perfect sense because I am because the proton is not going anywhere. So why? I mean, it makes sense to put the origin where the proton is. So already I'm making some use. An alternative would be to, set a system of reference somewhere around and having to specify the position of the proton and the position of the electron with two vectors. Or why having to introduce a new vector for the position of the proton if the proton doesn't move? We might as well stay where the proton is as the origin of my reference frame. But there's an additional symmetry that comes immediately out when you plot the forces. The only two ingredients that are there are the force, the Coulombic force, and the position. Now the point is, the Coulombic force is not, it's not just any force, like, I don't know, this force here, let me call it W. It has a specific feature. It points on the same line of the position. It's a centripetal force. It is a radial force acting in the direction of the center. So the important thing here is that F is actually parallel to R as vectors. And in fact, you can notice this because the vector R, if this is my unitary vector pointing in the direction from the proton to the electron, the vector R is just the length of this vector, which I will draw here like this way, times the direction specified by this unitary vector u of r. Similarly, the Coulombic force is the negative of this unitary vector times e squared divided by this square. So these mathematical expressions clearly show that the two forces are, in fact, parallel, or better actually, anti-parallel in this case, but they lie on the same line. So you see, there is likewise, in analogy with examples of the rolling particle along the cliff, there is an intrinsic natural reference frame, and is one in which one of the coordinates, one of the axes, points always from the center to the instantaneous position of the electron. So rather than using Cartesian coordinates, let me redraw this to make it clear in the picture. We can use a different set of coordinates. So we can use rotating coordinates. So let me explain what it means. One choice would be set y and x here, and then let the x, y, and z, and of course z, position. And then follow the three-dimensional motion of the electron by looking at the motion of the electron by studying individually each of these three coordinates. And this would be somewhat the equivalent of solving the problem of the cliff in the non-efficient reference frame. So the question we are trying to ask now, is there a more efficient reference frame to look at? Well, clearly, one piece of information we have is that the force is central. And therefore, if the force is central, major simplification come in, which will suggest a better choice of coordinate. But the centrality of the force, if you go back on our previous lectures, will imply two main results. The first result, the mechanical energy is going to be conserved. Why? Because remember, whenever you have a central force, the work exerted by this force on a particle does not depend on the path. And therefore you can define a potential energy. And therefore you can combine the potential energy with the kinetic energy and score that the mechanical energy is conserved. So the first piece of information we have that follows from the fact that the force is central is that the mechanical energy is conserved. And the second piece of information is that, remember, the angular momentum of the particle is going to be given by the vector product, the change in angular momentum of the particle in an infinitesimal time interval is given by the torque of the force, but the torque of the force is zero for a centrifugal force, for a radial force. again implying that also L is conserved. So why have, how do these two conservation laws guide us in choosing a better reference frame? Well, let's forget for a moment the first conservation law, which will come handy later. Let's focus on this conservation law. Well, one thing that this conservation law is telling me is that the motion of the electron occurs on a plane. Orbits lie or are confined on a plane. Why is it that? Well, think about it. Suppose the orbits were not confined on the plane. Let's work by absurd. It means that, say, initially, I can think my orbit to be drawn by a piece of arcs, which can be drawn on this plane. And some later time, the plane that contains a small amount of trajectories is a different. Now, this would imply that the angular momentum of the particle would have changed direction, because remember, angular momentum is given by the mass times velocity, r cross p, which means this. So, since this inner product defines a plane, if you change the plane where the particle is having its trajectory over time, then necessarily you're changing the direction of the angular momentum. So you're staying on in this plane at time t, you're going in this plane at time t plus delta t. This is my v prime, this is my v instantaneously. If the plane that contains these little pieces of trajectory is evolving with time, then clearly so does the angular momentum of the particle. But since the angular momentum of the particle is not changing, not only in modulus, but also as a vector, in particular, it is not changing direction. So the fact that L doesn't change direction implies that the motion is confined on a single plane. And why is this important? Because if you're on a plane, you only need two coordinates. Well, you're still embedded in a three-dimensional space. This simply means that the third coordinate can be chosen to be the distance from this plane. And if this is set to 0 at time 0, it will remain equal to 0 for the rest of the dynamics, just as much as the x prime coordinate in the cliff has trivial meaning. The distance from this plane will be stuck to its initial value, and therefore be trivial. So already the use of angular momentum conservation enabled us to go for a 3D problem to effectively a 2D problem. Which is already a big simplification. You have one less differential equation to solve. So, okay, this is already something which we have gained. So now from this point on, we can draw the electrons are orbitating around the nucleus as a trajectory on a plane. We can use a piece of sheet to draw this, And, whenever you see this kind of drawing for the atoms, it's kind of a symbol of the atom, you always draw this way, which is basically the picture behind the classical theory of the atom, which will turn out to be a wrong theory. So it's kind of interesting that the symbol of quantum mechanics sometimes used, which is electrons around the proton is actually a symbol that represents the failure of classical mechanics rather than the success of quantum mechanics. Okay, but this is not very relevant for the present discussion. I just find it quite funny. But anyway, I have my protons sitting in the middle, and now I can draw the electron on a piece of sheet. Let me rewrite the title. Because I know that whatever will be the trajectory of the electron, it will lie on this plane. Now, I want to make use of the symmetry now. And I want to make it, and try to get a better choice of coordinate. And this will be one in which one of the axes will be always pointing in the direction of the electron from the proton. So it will be U of R. Now, since I've now reduced the problem to effectively 2 dimensions, all I need to specify is a second reference frame, a second axis, preferentially orthogonal to the first one to make calculation system simple. So we will choose the only natural choice is we will call the U theta the second axis that we're going to fix it. So you see, my electron is sitting here, and I'm using, at some instance, and I'm setting 2 instantaneous versors or unit vector to specify a reference frame. But the electron is not going to be still and sitting there forever. At some later time, it's going to be found, say, in this R prime coordinate. And now, unlike I like the example of the particle rolling down the cliff, now also the system of reference will rotate, will adjust to follow the particle, because the system of reference here is not supposed to be still and let the particle go. Is defined by being always, one coordinate is always following the particle in order to always to point in the direction going from the center of the nucleus to the particle. So at time U prime, at time T prime, I will have a slightly different set of coordinates, and will be one in which U R prime and theta R prime, U theta prime will be this one. So this is a rotating reference frame. Now, anytime you have a rotating reference frame, you're in a so-called non-inertial frame. Remember, an inertial frame, the concept of inertial frame is key to quantum classical mechanics. It was introduced, if you want, by Galileo before Newton's laws were discovered. And it basically defines the concept of relativity. If you know a reference frame in which forces are not there, and you get a reference frame, and you get another frame which moves of still drift velocity with respect to this first frame, then in this new frame, this is called an inertial frame, because the laws of physics cannot distinguish whether you are in absolute quiet or still configuration, or your motion, or if you're moving this constant velocity with respect to another frame which is defined to be still. So the concept of inertial frame in classical mechanics is quite cumbersome, because only shift the problem of defining what is still at the next layer. It really is rugging the mud under the carpet, because how can you say that the first initial frame was actually not in motion? And therefore, the people from the 17th century, they used the static stars as absolute definition of inertial frame. They say If I have a frame that is not in motion relative to the static star, and I have another frame in relative motion with constant velocity to my initial frame, that is an inertial frame. But now we know that the static stars is a completely illusory concept. Stars are not static at all. So there is no absolute definition of a frame. That's precisely the key concept of relativity. But we should not go into that respect because that detail, because of discussion, because this is clearly not an inertial frame because you are actually rotating the frame as you move in time. And anytime you have a rotation, the velocity, the vector changes in time, right? Because before it was here and then it was there. And you're changing the velocity and changing, a rotation actually involves a change of velocity, which means essentially you have an acceleration. So a rotating frame is not an inertial frame. An inertial frame moves along an horizontal line in constant motion with respect to another one that is a rotating frame is not inertial. Violation of inertial frames, the fact that the initial frame is not inertial. I don't know if inertial in English goes with two N's. I think it goes with one. I don't know. Fine. I'm clearly not a native speaker. The fact that I have not inertial frame will come at the price of having centrifugal force. So basically, we are in the same situation of having, the famous example of inertial frame where you have, one of those rotating platform for kids at the kindergarten, and you have the classical example of a small kid. Okay, I'm drawing. Really, this shows how bad drawer of a drawer I am. So let me put here. My kid trying to walk towards the center of the rotating platform, hence experiencing a force that is not due to any physical body exerting the force, but it's due to the fact that I'm not in an inertial frame, and these are called apparent forces, which follow from the fact that you are in a more rotating frame, right? And therefore, as you get closer and closer to the center, you get this force, and you have to make an effort or actually do a work in order to reach the center of the rotating frame. And the same principle is used on the space stations to simulate gravity, right? That's why you get rotating pieces of the space stations, because by rotating, the people standing in a rotating frame experience a centrifugal force. This is a space station rotating in this direction. There will be a centrifugal force, and this centrifugal force can be tuned. The strength of the centrifugal force depends on the mass of the particle. It can be tuned by setting the velocity of rotation in such a way to be close to gravity, to produce an acceleration close to g. That's why in some sci-fi movies, you see people walking in their space station, like if there was gravity. And this is actually being used also when the astronauts train for space missions, because they go through very strong accelerations, and the way they train them is by putting them in very fastly rotating reference frames, which will generate a centrifugal force much stronger than g, which will help them being acquainted to what happens when they lift off to space. So I'm doing all of this discussion to say that we expect a centrifugal force. So there is a price to pay in choosing this frame. But is it worth it? Is the price worth the mathematical complicacy of choosing? Is the price you pay for using the simple mathematical description based on rotating frames, which is arguably going to lead to simpler equations, worth the price of having to produce centrifugal forces? We should see. So now we have already used a piece of angular momentum conservation, the conservation of the direction of angular momentum. Now, rather than writing Newton's equations, we write conservation of energy. Remember, we had the discussion in the past, using concepts such as energy or momentum, you're able to solve problems that would require solving differential equations. So we want to do the same thing. Because you see, how much can we take out of this conservation, which we haven't already? In other words, we had 4 conservation laws. 3 components of angular momentum, 1, 2, 3, plus 1 component of energy. Now, we already used one of them, which was used to the conservation of the direction of angular momentum. And that already was used to reduce the problem from 3-dimensional to 2-dimensional. Fine, now we have 2 more variables to fix. But we have still quite a few conservation laws to use. We can use those coins, the conservation laws, to further simplify the problem without having to solve differential equations. So let's do that. Let's write the energy of the system. The energy of the system, which is going to be conserved, will consist of the kinetic energy, which is 1/2 mass velocity squared, that I write in the following way. This is my velocity, plus my potential energy for the Coulomb. Now, the potential energy only depends on the radius r, defined as the modulus of the vector r, because remember, the potential energy for the Coulomb, this we haven't discussed. How we got into this. Because if I were to discuss it now, I would have to introduce the concept of gradient, which you haven't yet seen in Andrea's course on mathematical backgrounds. For those who are not taking the entire course, they're not students from the QCD degree, there is a parallel ongoing course on mathematical methods in which we develop concepts that are used in the course. You know, in this lecture, I am not assuming that you already have seen symbols like this in your background. This is called the gradient. So if you had seen this, you would be able to see why the potential energy associated with the Coulomb force is what it's going to be writing now. For the moment, just, it suffices to say that if I use this expression, then it follows from computing the work done by the Coulomb force. Okay? So, this is my mechanical energy. The mechanical energy will be this. So it is going to be 1/2 m d r squared dt squared And we know that this guy will remain constant throughout the motion. And I want to make use of this fact. And the way we do so is by taking one next step into writing this expression slightly differently. So this is the velocity. So let me draw it again. Now, this is the velocity of my particle. And this is the modulo square of the velocity of my particle. Now, let me draw the velocity of the particle in some arbitrary instant as a vector. And the square, now, rather than using Cartesian coordinates, I remind you we are using polar coordinates. Now, if I write polar coordinates, then I can define a component along u theta, let me call it v theta, and a component along vr. And therefore, I can use this splitting and write the following. Yeah, so this is still a two-dimensional expression because I have two variables, theta and r. So it looks like we have not yet done much progress. Now, here comes the second major simplification that comes from the conservation laws that I discussed before. So to see our conservation of angular momentum, we want to use the conservation of angular momentum here to simplify the expression stating the conservation of energy. We want to use this second coin. So actually it's the third coin. We use one coin for the plane. We use a second coin, which is writing down that this quantity is going to be conserved, the energy. Now we're going to use the third coin, which is using again the conservation of angular momentum to simplify this expression. We can use it twice because the conservation of our angular momentum is actually three equations. So we only have used one of them. We have two more. And we can just need to use one more. So in the next lecture, I will show how the conservation of angular momentum will enable us to further simplify this expression and go into an equation that can be solved and give us information about the orbits of the electrons around the probe. So, quite a few concepts to digest in this lecture. Don't be scared if they look a little bit overwhelming. I will review them in the next lecture, get the main points out, and then we'll take it from there. So, just try to follow this and we'll see in the next lecture how to move forward. Okay. Have a good